I'll start the recording. We're going to do double integrals over general regions. So let me just go right to figure 5 here. I want to show you there are two regions that we're going to be dealing with here. There are type 1 regions and type 2 regions. Those are our general regions. So, okay, so, and you know the context, You have a surface, a function of xy, and you are interested in finding the volume between that surface and the xy plane over some region D. Okay. Now, you notice in the picture here, the region D is not a rectangle. Okay, in the picture, I mean, you can see they've put a blue rectangle around region D, but the region D is not a rectangle, right? So what would a double integral look like? Well, first of all, before we get there, let's talk about some type 1 regions. So type 1 regions are where you have a region D in the xy plane, and you have like you see there on the left there, you have a region D, the left picture in figure 1. The x limits are a and b, and you're bounded above by the function g2 of x. Okay, that's a g2 of x. And you're bounded below by function g1 of x. Okay. How many remember in calculus 2 finding areas between areas of regions where the top and bottom function were different, like functions? Now we're doing volumes, but how many remember seeing regions like that in calculus 2, like in figure 5 there? Okay, Ellie recalls it. And Charles, okay, so, well, and you know, and then they give 2 other pictures of a type 1 region. Again, type 1 region, you're bounded, the region D is bounded below by the function g1 of x and above by the function g2 of x. Okay, so then in terms of an integral, hold on. Let me just find it here. Hold on, I went too far, class. Yeah. This here would be how you find the double integral. So your y is, let me just show you maybe on the whiteboard real quick here. I want to show you something. So I think this will help. Let me just do this before we. Okay, x-axis, y-axis. Okay, a function g2 of x and a function g1 of x. Here's A, here's B. Okay. And I want to say this the right way. So if you think about your top and bottom limits, okay, your top and bottom limits, okay, and this by the way is your region. I got to draw it. your region D. So the double integral, over the region D of f of x, y, dA. Well, now dA just means that we've not committed whether we're going to do dy dx. I mean, dA could be dy dx or dx dy. But the way that this type 1 region is, okay, the top, I mean, you know, you're going to have 4 limits here, right? You're going to have 4 limits here. 4 limits. You know, you're going to have limit here, limit here, limit here, limit here. 4 limits. So if it's a type 1 region, you're going to go do dy first. You're going to integrate with respect to y first. Well, then you need here, you need a bottom limit, and here you need a top limit. Well, what's the bottom limit? What's the bottom limit? Well, it's not going to be a constant, because if you had a constant, okay, that would mean like if you had a, you know, if you had something, well, maybe I'll draw it. If your region were this, okay, you'd have, like, you know, y equals d, keep this separate, y equals c to y equals d. In other words, you're bounded below by a function. It's just a constant function, y equals c. You're bounded above by a constant function, which is y equals d. Okay, so like what you're used to seeing is this. Right? How many remember, how many are very used to that from section 12.2? Very used to this kind of integral. Maybe give me a thumbs up if you're, well, actually you haven't done section 12.2 yet, have you? I forgot, that's not due till Wednesday, right? But what I'm trying to say is, for a type 2, for like a section 12.2 integral, when you have constant limits, when you have these constant limits here, D and C, really you have a type 1 region. It's just your bottom function is y equals c. That's a constant, right? A horizontal function, a horizontal line. And the top function's the horizontal line y equals d. It's really, but now what we're doing is we have functions on that bounding functions on the top and the bottom of our region D that are functions of x. I mean, what I mean is they're variable functions of x. So let me ask you, what's going to go in this bottom circle here? What's the bottom limit if we're doing dy dx? What's the bottom limit here? Okay, but what am I gonna put in there? G1, that's right. Good, Charles. G1 of x goes here. What's going to go up here in the top limit? Your top y limit. Good, Charles. Good, Ellie. G2 of x. Right. So G1 of x and G2 of x. What about your dx? What are your x limits going to be? What's this limit going to be here? Right, going to be A. And then the top limit's going to be B. Okay, so this is really just I mean, it's a continuation of section 12.2. Section 12.3 is just a continuation of section 12.2. It's just your limits are your like for a type 1 region, your y limits are variable functions of x. And that's how if I go back to the thing here, that's how they're getting this this double integral for type 1 region. Are there any questions on that? Who's feeling good so far? Maybe give me a thumbs up if you're feeling good so far. Okay, good. Charles and Ellie are good. It's Malik's good. All right, good, good. Well, then let's continue on. Let's continue on. Okay, Juliana's good. Excellent. So, well, I guess you know that if we have a type 1 region, sure enough, there's going to be a type 2 region. Type 2 regions are where the region D is bounded on the left and the right by functions of y. Okay, by functions of y. And so let me ask you, if you're going to do a double integral and you have a type 2 region, are you going to integrate with respect to x first or with respect to y first? What do you think? Well, let's take a look. Let's take a look. Let's take a look. So if I go to the whiteboard here, hold on. If I go to the whiteboard, here's x, here's y. Okay, I'll draw. It's not pretty, right? But you get the general idea. Okay, here's D. Here's C. This is, well, we're not going to use G now. We don't want to get confused because we use G functions for our for boundaries for type 1 region. Let's use H functions. This H of 2 is a function of something. H of 1 is a function of something. What's H2? This is H2 right here. What's that? That's a function of what variable? X or Y? Function of Y. That's right. And similarly, good, Ellie, H1 is also a function of Y. And so, if you're going to do your integration, okay, you're going to be going from a function on the left to a function on the right. So, based on that, do you think we're going to integrate with respect to x first or y first? Now, think of it like this, class. H2 of, well, yeah. if I were to, yeah, I want to see. This may not. I mean, the double integral. Hold on. Okay, so now we have a double integral over region D, f of x, y, dA. Okay, so if we're going from this function on the left to this function on the right, if those are our boundary functions, and they're functions of y, okay, I'm going to put the h1 of y here, because it's the left function, the h2 of y here, because it's the function on the right. Can I put, let me ask you this, can I put a dy here? Can I put a dy there? Is that right? No. No. You're going to put a dx there, because h2 of y is well, you're going, think about, you're going in the direction of the x-axis. You got a function on the left, a function on the right. Look at the arrows. Look at these arrows. And I'm doing this to help you just kind of remember what to do. The arrows are going in the direction of what axis? Those red arrows that I'm drawing. From the left function to the right function. They're going in the direction of what axis? The x or the y? The x. So you do dx. And then you do dy. That's right. Good. Now, let me just see here. One moment. There may be, yeah, C and D here. Okay, are there any questions on this? This is a type 2 region. This is type 2. And I think once you get some practice with integration, this will make, I think you'll be more comfortable. But now what we need to do are to do some problems. So let's go ahead here and let's go ahead and do some problems. Let's look at a couple problems here. So the book has good problems. I'm going to add to that variety with my own. Let me give you a moment to copy the example down. Okay, so when we do a double integral here, okay, when we do a double integral, naturally we want to iterate the integral. Like this. And can you find an antiderivative of the sine of y squared? What do you think? Is it possible to do that? So Charles, if you, okay, any antiderivative, if you differentiate it, you should get the sine of y squared back. Charles is feeling you can't do this, and he's right. You cannot integrate this. To my knowledge, that cannot be integrated. That inner integral. But yet they're saying evaluate it. They're saying evaluate it. So this, we're integrating with respect to y first and then x. So there's a region D of integration, okay, that goes with this double integral. Is the region D the way, if we're doing dy first and dx second, if we're integrating with respect to y first and x second, are we treating this region as a type 1 region or a type 2 region? When you integrate with respect to y first, you're treating your region as a Charles, you're almost right. It's a type 1. But thank you for trying. I got it. Charles tried. 50-50 chance, So he did better than than the rest of you, because he volunteered an answer. Yeah, it's a type 1 region. But the problem is we can't, I mean, we can't integrate this as a type 1 region. So we have to make our region D a type 2 region. And in order to do that, I really need to draw the region. I really need to draw. So when I see like x here, when I see x, I think, okay, that's y equals x. That's my bottom limit there. When I see 1 here, I think, okay, that's y equals 1. So this region D is bounded below by the line y equals x. It's bounded above by the line y equals 1. That's a horizontal line. And x goes from 0 to 1. So what we're going to do, let's go ahead and go to the next page here. Okay. We're going to reverse the order of integration. Reverse the order of integration. Okay. And what I've done on the left, again, I find pictures very helpful. So on the left here, I've drawn my region D as a type 1 region. And it's a type 1 region because I'm integrating with respect to y first. Okay. But as a type 2 region, okay, I would be integrating with respect to x first. And so I'm using functions for type 2 region. I'm going to use functions on the left and the right as my boundary functions, you know, for to start with. Take a look at the two pictures there. You know, here's the type 1 region. Here's the type 2 region, and let me know if you have any questions. Please let me know. All right, well then the integral here that we're interested in can be rewritten as this double, I should say the double integral. It can be rewritten as this double integral. So I'm saying integral, but of course I mean double integral, right? So you see now, if I integrate with respect to x first, I'm going from my function on the left is x equals 0. My function on the right is x equals y. And so that's how I get x equals 0 here and x equals y here. Bottom and top limits. And then y goes from 0 to 1. And we want to see now if this helps us get our answer. Sometimes you have to do this. Just because you know you're being presented with a double integral, you might have to change the order of integration, or you might have to just figure out what from the scratch what the right order of integration is. All right, may I go to the next page? Is everybody ready to go to the next page? Pretty close. Okay, Ellie, good, good. Juliana, good. What's the antiderivative of the sine of y squared with respect to x? In the inner integral, good, good, excellent, excellent, Ellie, excellent, Charles. Hinu, let me just say, the inner integral, right, when we integrate with respect to x, we're treating the sine of y squared as what? In the inner integral, we're integrating with respect to x, so the y is treated as what? We treat the y, it's the same as with differentiation, taking derivatives. When we integrate with respect to x, okay, we treat the y as a what? As a can you remember the word? As a constant. That's right. So for instance, if we take the partial derivative of a function with respect to x, we treat the y as a constant. It's the same for this inner integral here. We're integrating with respect to x, so we treat the y as a constant. So the antiderivative would be the sine of y squared times x. And that's what we have here. So we'll put in the y and the 0, those top and bottom limits for x, which we do here. And this gets us down here. Let me give you a moment to catch up. Let me know if there are any questions, please. All right, well, now here we can let u equal y squared. We can do a substitution. And you know, naturally for these double integral problems, you know that like I'll want to see your work. I mean, this will be for exam 3. I mean, I always want to see your work on any exam, right? But these integrals, you know, I'm going to want to see your work. That's part of your showing your work's part of your grade. I have to see that. Well, it's just expected. You know what I mean. You know what I mean. And you know, based on the first exam, you are showing work, right? You're showing your work. So okay, we make a change. We go from an integral with respect to y to an integral with respect to u, and so naturally the y limits change to u limits, since u equals y squared. When y equals 1, u becomes 1 squared, and when y equals 0, the u limit for that, corresponding u limit would be 0 squared. And so we're going to be able to find the answer to this problem. Okay. May I move to the next page? Are we good? Okay. Charles is good. All right. Madeline's ready. All right. Okay, Ellie's good. Malik's good. All right, well then let's go to the next page. And Juliana's good, excellent. So now it's just calculus 1 problem. And this is going to be the final answer. And you know WebAssign wants the answers in simplified radical form. So I'm going to keep the cosine of 1 as the cosine of 1. 1 is an angle in radian measure. Okay. So being able to compute double integrals, and you'll learn soon about triple integrals, being able to compute these is important when we get into chapter 13, because a lot of applications, important applications, for instance, in physics, you can relate the applications to double and triple integrals. Things like surface integrals and flux and things like that. Work, for instance. So it is, this isn't just you're not just doing this for, you know, to do something interesting. It is interesting, but there are very important applications, and that's why you need to be able to become proficient at computing double integrals. All right, and in the future, of course, triple integrals, but let's one thing at a time. I'd like to do another example before I let you work a little bit on section 12.3. All right, I'll move to the next example if we're good. Okay, let's look at volume. Okay, let's look at volume. Volume of a tetrahedron. So let me give you a moment to copy this example down. All right, so let's see what's going on with this problem. So remember how I had mentioned to you that double integrals are used to find volumes. And you do have an intuitive feel for that, because the double integral derives from a double Riemann sum, where you add up the volumes of a bunch of bricks over some region in the xy plane. And so, you know, single integral, of course, can be a definite integral, can be interpreted as area. Double integral can be interpreted as volume. So here we want to find the volume of the tetrahedron enclosed by, well, we have a plane here, x plus 2y plus c equals 2, and then another plane. Okay. Let me ask you this. Would x equals 2y, would that plane be a plane that is horizontal or vertical? That's right, you know, it would be a vertical plane. Because if you think about x equals 2y, right, the z is unbounded. That's exactly right. Right, you know. So this plane goes up and down along the line x equals 2y or y equals x over 2. Now what about the plane x equals 0? Is the plane x equals 0 a horizontal plane or a vertical plane? It is a vertical plane. Good, Juliana. As a matter of fact, what coordinate plane does x equals 0 correspond to? That's right. Good, Charles. All right, Marwan, good. The YZ plane. That's the YZ plane. That's what x equals 0 is. And incidentally, z equals 0. What plane would that be? Good. That's the xy plane. So you have this solid that's bounded below by the xy plane in the back by the YZ plane. On the side by x equals 2y, that plane. Okay, and then this plane here can be written as z equals 2 minus x minus 2y, right? So would that plane where would that plane bound this solid? This bounds the solid, that plane, which is neither a vertical plane or a horizontal plane. It's one moment. Let me make sure I got the word right here. It's an oblique plane, right? So that's going to bound the solid, the plane x plus 2y plus z equals 2, which can be written as z equals 2 minus x minus 2y. That bounds this solid on blank. Three letters I'm looking for. From above or on top. No problem, Charles. You have the right idea. Okay, so I'm trying to do a problem. You're going to have volume problems to do, and they take time. But I'm trying to, you know, I mean, I want to do one with you that requires a little more thinking, so it'll be helpful. So, okay, so let's look at this solid. Let's go to the next page. Okay, I've drawn the solid here. Here's the solid. Okay, and you notice that I have these points of intersection. The plane z equals 2 minus x minus 2y intersects the line y equals 1 minus a half x. I want to be careful here how I phrase this. One moment. So, you know, how am I getting these two points of intersection here? Well, those 2 points of intersection are when that oblique plane intersects the plane z equals 0. So when that happens, the plane z equals 2 minus x minus 2y and the plane z equals 0 are both true. Okay, when those where those 2 planes intersect each other, we can set those planes. We can. I mean, I'm going to say, when the 2 planes intersect each other, the z, wherever they intersect, the z values are in common, right, between the 2 planes. So that means that 0 at that where they intersect, and we know they're going to intersect in a line, right? We know those 2 planes are going to intersect in a line right here, right? So hold on, maybe I can get the yeah, the 2 planes intersect in a line. So that means then that, how do we find the equation of the line? Well, we set z equals 0 and set it equal to z equals 2 minus x minus 2y. And this is going to tell us then that y equals 1 minus a half x. And that's how we get this right here. So in other words, this line here has equation y equals 1 minus a half x. Okay. Now the plane, this plane, z equals 2 minus x minus 2y, also is going to intersect the plane x equals 2y, or y equals x over 2. The intersection, okay, will be in the xy plane, and it's going to follow this line right here. Okay, so what's the equation of that line? Well, when the plane z equals 2 minus x minus 2y intersects the plane x equals 2y at z equals 0, then we can just set z equal to 0 and substitute in x equals 2y right for this x here. Okay, and so that means then that I mean, basically what I'm trying to do is I'm trying to justify why this point here has coordinates 1, a half, 0. It's because it's where the 3 planes meet. Okay, so you have 3 planes that meet there. So they're all true. They're all true. So I can take the plane z equals 2 minus x minus 2y. I can substitute in z equals 0. I can substitute in x equals 2y, and then solve for y, and then solve for x. And therefore, that point of intersection is 1 half, is 1, 1 half, 0. Okay. Now, the other point of intersection, 0, 1, 0, that makes perfect sense, because when z equals 0, the plane z equals 2, well, when z equals 0 and y equals 1, maybe I'll write it in here. Okay. I mean, we know that this coordinate here, we know that when z equals 0, hold on, let me make that a little better. okay, we know that when z equals 0, okay, and when x equals 0, okay, that means 0 is equal to 2 minus 0 minus 2y. Trying to get this as good as I can get it. And therefore, y will equal 1. And that's how we get this 1 here. Okay? So I'm trying to show you in some detail why this is true. Now, what's happening is we have this region D here. The region D, I redrew it here. Okay? And if we treat the region D as a type 1 region, if we treat the region D as a type 1 region, which is the right thing to do, because if you treat the region D as a type 2 region, okay, you're going to need 2 double integrals, right? Because of the shape of that triangle. So as a type 1 region, then, based on the region D up there, we have our lower limit, which is y equals a half x, and our upper limit, which is y equals 1 minus a half x. Okay? And then the function, which is the z equals f of xy function, would be that plane on top, right? That's your surface. And you're finding the volume below, you're finding the volume between that surface above, that plane, z equals 2 minus x minus 2y. You're finding the volume between that plane and the xy plane over the region D. Okay, well, base 2 on the region D, my x limits go from 0 to 1. Therefore, I mean, this is just, I mean, you know, this is just really incredibly beautiful math, you know. How many remember the movie A Beautiful Mind with Russell Crowe about Charles remembers it. I'm trying to recall the Nash. Can't remember he got a Nobel Prize in economics, I believe. Dr. Nash. Can't recall. Should we know his first name? But you know, but he if you look in the movie, the stuff he like wrote on the stained glass windows and stuff like that involved like partial derivatives and integrals. I mean, this is the type of stuff he was doing, right? So you're really, you know, you're really learning good stuff here. Well, now what we have to do. So what? Incidentally, what I did just to be very thorough, I also wrote the volume as a type 2 region. And if you're gonna treat that region D above, that region D here, you're gonna treat it as a type 2 region. You're gonna have to add 2 double integrals because there's a split. There's a split here. There's a split right here, right? There's a split right here. So that means that the function on the right, here, you know, you got function. The function on the left is stays the same, but the function on the right changes after x equals. Hold on. I want to be careful how I phrase it. it changes after y equals a half. You get a different function on the right. You get this function here on the right. So you see the function on the right changes. It changes from this function to this function here, and that's why you need two double integrals. So which do you want to do? Do you want to treat the region as region D as a type 1 region, or do you want to treat region D as a type 2 region? Which is a better way to go, you think? Which volume do you want to compute? Volume 1 or volume 2? Okay. Looks like volume 1 is better. And again, this is the kind of thing that you'll need to be able to, figure out, So, okay, so I'm going to do type 1 region. May I move to the next page? Are there any questions? This is all in the recording, but I know you're taking notes, so. All right, Charles is good. Juliana's good. Ellie's good. Wonderful, wonderful. All right, Madeline's good. Well, if there are no objections, then I'll go to the next page and we will compute this double integral. Here we go. So we're integrating with respect to y first. The antiderivative of 2 minus x minus 2y with respect to y is going to be 2y minus xy minus y squared. Again, you're holding the x variable constant. So then I'm going to substitute in my limits, which are now functions of x. Well, they're variable functions of x. I'm going to substitute them in for y, and that gets me here. See, I wanted to do kind of a one that involves some work, so that you can say, well, if Dr. Duty did it, I can do it too, right? Right. I'm trying to model a good one. How many have had maybe a professor where the professor just kind of does the easy problems, and then when you do your homework, you're having to do like ones that are maybe some that are quite a bit harder? Okay, Ian knows what I'm talking about, and so I'm trying to do one that is well, hard or harder. So now this one here, there's a lot of math involved. If this were on exam 3, you might need the 4 attempts, right? But maybe not. But you might. But if you're careful, maybe not. This is just really algebra now. You just have to be careful with the algebra. So I'm going to distribute the the 2. I'm going to distribute the x. Okay. And I'm going to work it out, and I get down to here. And I'll just let you copy. How many have had a class maybe where a professor like does a lot of derivations and things, and then at the end gets to do a problem, does a problem? How many have had that situation? I used to have that when I was in college. Maybe the last 5-10 minutes, professor gets to an example. I don't know if you've had that, but and theory's good. It's good to talk about theory, but I think examples help motivate the theory. How many find that? When you understand examples, it helps you understand the theory. How many feel that way? Okay, Charles knows what I'm talking about. All right. Well, if I know you're taking the notes down. Ellie says she needs both, and I absolutely understand that. Absolutely understand that. So I'm trying to provide a balance. A balance. Um, absolutely. Okay. So when you do all your algebra, you get down to this step here. Let me know if there's anything you don't quite understand. There's a lot of nice simplification that goes on this step, which is good. And now it's a calculus 1 problem. All right, may I go to the next page? Are we good? Okay. Excellent. Excellent. Okay, so here we go to the next page. And the answer is going to be 1/3. That's the volume. That's the volume of that solid. That's the volume of that tetrahedron. That's the exact volume. So if, for instance, you're designing pieces of candy, candy comes in all different kinds of shapes. If the candy's in the shape of a tetrahedrons like that, you'd want to know the volume, the exact volume of each piece of candy, right? Because that means how much chocolate you're going to put in, costs money. How much does each piece cost? You don't want to know about how much each piece costs, of candy. You want to know exactly how much each piece of candy costs. Well, to know that, you have to know the exact volume. Are there any questions? So I know you have to, of course, practice these kind of problems, but so far, how many of you are feeling at least reasonably comfortable? Maybe not perfect, but reasonably comfortable about section 12.3. Okay, Charles is good, reasonably comfortable. Juliana, Gordon, so far so good. Okay, excellent. This is what I like to hear. Ellie too. All right, Malik, good right now. Excellent, excellent. All right, well then I'm going to stop the recording.